in this section, we're going to look at some techniques that we can use to integrate expressions like this, where I have sine to a power times cosine to a different power, or secant to a power times tangent to a different power, assuming that these powers are positive integers. Okay. First, I want to review a couple of trig identities that are going to be useful to us. It's one that I think you're probably very familiar with already. We can also use this one that's called the power reducing formula. And here's another one that is a power reducing formula, for this time for cosine. Okay, so these are formulas that you should, if you don't remember them already or they're not already in your booklet, go ahead and put those in. Okay, we're going to work first with sines and cosines. And I want to give you some guidelines to use when we try to reduce powers of sines and cosines. Okay, we'll be working a problem for each of these guidelines. The first one is, if the power of the sine is odd and positive, save one sine factor and convert the remaining factors to cosines. So we want to end up with sine x times some number of cosines. Okay. When the power of the cosine is odd and positive, save one cosine factor, convert the remaining factors to sines. Then you can expand and integrate. When the powers of both sine and cosine are even and non-negative, make repeated use of the formulas that we had up here for sine squared x 1 minus cosine 2x and cosine squared x 1 plus cosine 2x, both over 2. Okay, we want to change the integrand so we have odd power of the cosine, and then use the second guideline. Okay, and these guidelines are found on page 532 in your textbook. Let's take a look at a problem where the power of sine is odd and positive. Okay, we can see here our power of sine is odd, power of cosine is even. Okay, we're going to change two of those sine squareds to cosines by doing this. We're going to have sine squared x, cosine to the fourth x, and then here's our third sine. Okay, now I'm going to use the Pythagorean identity and change that sine squared x. And this is going to be 1 minus cosine squared x times cosine to the fourth x sine x dx. Okay, now we're going to multiply all my cosines together. So I'm going to have cosine to the fourth x minus cosine to the sixth x times sine x dx. Okay, I'll now break this into two integrals. Each of these integrals now is something that I can integrate, but I do want this sine x to be negative, so I'm going to take that out, take a negative out of each one. And since this one was previously subtracted, when I take the negative out, now it's added. And now I integrate. Okay, in this example, both of the exponents happen to be positive integers. This strategy will work as long as either m or n is odd and positive. In this next example, the power of cosine will be 3, but the power of sine is negative 1/2. But we can still use similar technique. Okay, in this problem, we've got this curve, cosine cubed x divided by the square root of sine x. And it looks like we're trying to find maybe the area there. Okay, and we want to save one cosine to use as our derivative when we integrate. We're going to take the integral from pi over 6 to pi over 3, and we're going to change that cosine cubed x to cosine squared x times cosine x divided by square root of sine x dx. Now we're going to change that cosine squared, use the Pythagorean identity again. That's going to be 1 minus sine squared x times cosine x divided by the square root of sine x dx. Okay. Now we're going to divide each of these terms by that square root of sine x. And 1 divided by that will give us sine x to the negative 1/2 power. And then this divided by that will give us sine x to to the 3/2 power times cosine x dx. Now when we integrate, I get sine x to the positive 1/2 power divided by 1/2 minus sine x to the 5/2 power divided by 5/2. And we are evaluating from pi over 6 to pi over 3. Okay, when we bring this up, that ends up being 2 times square root of 3 over 2 raised to the 1/2 power minus 2/5 square root of 3 over 2 to the 5/2 power minus the square root of 2 plus square root of 32 over 80. If I put that all in the calculator, I get approximately 0.239. And again, that would be the area of this region in the picture. In our next example, we're going to look at what happens if the power is even and non-negative. So we're going to be looking at this problem. And we're going to replace this cosine to the 4th x like this. And now we're going to multiply that out. Get 1/4 plus okay, now we're going to use the power reducing formula. So the first two terms remain the same. And the third term becomes 1/4. 1 plus cosine 4x over 2 dx. Okay, rewriting, we get 2 cosine 2x dx plus 1 over 32 times the integral of 4 cosine 4x dx. And now we integrate. So this is going to be 3/8 x plus sine 2x over 4 plus sine 4x over 32 plus a constant. In this example, if I were to evaluate this, say, from 0 to pi over 2, I would see that this first term would be 3 pi over 16. This would be 0. This would also be 0. And then evaluating at 0, all three of these would be 0. So the only thing that really mattered was that term evaluated at pi over 2. Okay, there was a mathematician, John Wallace, who noticed this and came up with some equations that we can use kind of as a shortcut if we're in this situation. These are in your textbook on page 534, but I'm going to write them on the board for you here. If n is odd, and we'll say that n has to be greater than or equal to 3, so it doesn't apply if n is 1, then the integral from 0 to pi over 2 cosine to the n x dx is equal to 2/3 times 4/5 times 6/7 until we get up to n minus 1 over n. And the second equation is like this. If n is even, and again we're going to stipulate that n has to be greater than or equal to 2, then this integral is equal to 1 over 2 times 3 over 4 times 5 over 6 all the way up to n minus 1 over n times pi over 2. Okay, so just a couple little shortcuts that might help you every once in a while. Next, we're going to turn our attention to integrals that are written as products of secants and tangents. And we've got some guidelines for those. These are given to you on page 535. Okay, if the power of the secant is even and positive, save a secant squared factor and convert the remaining factors to tangents. Then expand and integrate. If the power of the tangent is odd and positive, save a secant tangent factor, convert the remaining factors to secants. Then expand and integrate. When there are no secant factors and the power of the tangent is even and positive, convert a tangent squared factor to a secant squared factor, then expand and repeat as necessary. Okay, when the integral is of the form secant to the m power x dx, where m is odd and positive, use integration by parts, as illustrated in example 5 of the last section. Okay, if none of these guidelines will work for the problem you were working on, try converting the secants and tangents into sines and cosines. Let's work an example. Okay, we can see in this example that the power of the tangent is odd and positive. So we're going to use our second guideline. Save a secant tangent factor, convert the remaining factors to secants. So we're going to rewrite this a little bit. Go ahead and bring the secant up with a rational exponent. Okay, I want a secant tangent factor. So I'm going to have to reduce this exponent. So that I can add another one in just a moment. And I reduce this from tangent cubed to tangent squared. So now I can have secant x tangent x as a factor. Now I'm going to change this tangent squared to secant squared minus 1. So now I have secant x to the negative 3/2 times secant squared x minus 1 Okay, now we're going to multiply these two terms together. So negative 3/2 and squared is just going to give me positive 1/2. And then I still have my secant tangent here. And now I'm ready to integrate. Gives me 2/3 secant x to the 3/2 power minus 2 secant x to the negative 1/2 power plus my constant. In our next example, we're going to have a problem where the power of secant is even and positive. And here it is. Okay, we're going to take secant squared 3x out separately, which gives us secant squared 3x tangent cubed 3x times another secant squared, 3x dx. Okay, now I'm going to change this secant squared 3x to the tangent form. So I'm going to have 1 plus tangent squared 3x times tangent cubed 3x and secant squared 3x dx. Okay, I'm going to multiply this out. I bring out a 1/3. I have tangent cubed 3x plus tangent to the 5th power of 3x. Okay, and because I took out this 1/3 here, that allows me to put a 3 in here with my secant squared 3x dx. Okay, now I'm ready to integrate. Get 1/3 tangent to the 4th of 3x over 4 plus tangent to the 6th of 3x over 6 plus a constant. I can multiply this back through, and then this would be, instead of 4, that would be a 12, and 3 times 6 gives me a denominator of 18 here. In our next example, we're going to look at what we can do if the power of the tangent is even. So we're going to look at that's the equation of this curve here. We want to find the area under that curve between 0 and pi over 4. We're going to integrate from 0 to pi over 4 tangent to the 4th power of x dx. To work this integral, I don't have any factors of secant, so I'm going to take one of the tangents squared, so 2 powers of tangent, and convert them to secant. This gives me integral from 0 to pi over 4 of tangent squared x times secant squared x minus 1 dx. Now I'm going to rewrite this as 2 integrals. First I'll have tangent squared x times secant squared x dx minus the integral of tangent squared x dx. Now I'm going to leave this first term the same, this first integral. But for this one, I'm going to do the same thing that I did up here and rewrite this as secant squared x minus 1 dx. Okay, now this integral is going to give me tangent cubed x over 3 minus tangent x plus x plus a constant. Okay, and we need to evaluate that from 0 to pi over 4. So our final result is going to be 1/3 minus 1 plus pi over 4, which is approximately equal to 0.119, which would be the area under this curve. Okay, the last option in our guidelines for secants and tangents was that if we can't get anything else to work, we could take secant tangent integrals and convert them to sines and cosines. Let's take a look at how that works. So I've got the integral secant x over tangent squared x. I've tried everything else. Nothing applies. So we're going to rewrite this. I'm going to write secant as 1 over cosine x. And the tangent squared is in the denominator, so it's going to be cosine squared x over sine squared x dx. Okay, so I've got a cosine here, 2 cosines up here, so I'm going to cancel those out. And now I can rewrite my integral as sine of x to the negative 2 times cosine x dx. And when I integrate, I get negative sine of x, the negative 1, plus a constant. And you can go ahead and flip this over and make cosecant x plus a constant, negative cosecant x. Okay, the last technique we're going to use with these trigonometric functions is to use a product to sum formula to simplify our work. Okay, the formulas that you should know for sine and cosine products can be found on page 537 in your textbook. Let's look at a problem where we can use these formulas. So I've got the integral sine of 5x cosine 4x dx. And I can rewrite that as 1/2 the integral sine x plus sine of 9x dx. which gives us 1/2 times negative cosine x minus cosine x minus cosine 9x over 9. Plus a constant. Okay, we're going to multiply this through. So we have negative cosine x over 2 minus cosine 9x over 18 plus the constant. Okay, that's all for this section. I know that's quite a bit. And once again, the way to get better at these is to work more problems and practice.